So peripherals programming on Raspberry Pi. This is the topic. So Raspberry Pi is actually a series of single board computer, small single board computers developed in the United Kingdom by a Raspberry Pi Foundation long ago. Basically, this was created to promote teaching of the basic computer science in schools. Then, actually, what happened is this Raspberry Pi became very attractive hardware in terms of robotics, and they also wanted to make a smaller size of Raspberry Pi in terms of form factors. And then they created the various, form factor versions to cater into IoTs and robotics and all these domains. So then they felt that, okay, we need to add the Wi-Fi, Bluetooth connectivity, and so all these additions happened, and various series of Raspberry Pis came. And I would like to actually focus only on a Raspberry Pi Zero W, which is basically with Wi-Fi and BT enabled. Whenever I have to do a peripheral programming, I need to know the internals of the hardware. So in order to work on any of the hardware board, we need to know the internals of the hardware, the capability of the processor, capability of the interfaces what we have. See, the core of the Raspberry Pi Zero is actually an ARM processor. Technically, Raspberry Pi is not a controller. It's basically a single board computer. It uses 1 gigahertz Broadcom chipset, SoC 2835. It has 512 MB RAM, and it is based on ARM 1176J processor, which is basically from ARM 11 family with ARM V7 architecture. There's various peripherals integrated. If you see, the Bluetooth is integrated in Raspberry Pi Zero W, Wi-Fi is integrated, the various IOs, GPIOs are integrated. So when I say IOs, I2C, SPI, basically the low speed protocols are supported. Then the power adapter, then the SD card, then the HDMI, and the camera sensor interfaces. All these interfaces are there, and the resources provided by Raspberry Pi, basically it is a part of the BCM2835. It could actually use the SoC's peripherals, processor peripherals. Sometimes an additional hardware or controller is added to drive the additional peripheral devices. So the core BCM2835 SoC supports timers, interrupt controller, GPIOs, USB. Then the IOs are actually also PCM compatible. The DMAs, pulse width modulation, all the GPIO supports PWM. Then there is a UART. So when I do a development, what will happen is Raspberry Pi will be connected with it has an USB port. I will connect a USB hub there. Then I will connect the keyboard and mouse to those USB hub, and I will connect the power adapters and the HDMI monitor, and we will have usually an SD card where the Raspberry Pi, the operating system is loaded, so that when you power on the normal Linux PC, how you see, in the same way the system will boot and you will get a Linux shell, and then you can do all the type of programming to handle all the hardware devices. It's a typical single board computer. So now I will go basically into the compatibility. See, in order to do a peripheral programming, we need very well know the hardware compatibilities first. So when I say hardware compatibility, what I mean is how I can connect various hardware with the various IO devices, various interfaces. Also, the use of various protocols. So if you see, there could be sometime LCD screen supports some protocols, some interfaces, GPS supports some interfaces and some protocols. Then the sensors and motors, they also support sometimes the IO, sometimes they use the analog inputs. So Raspberry Pi will allow you to connect the various interfaces, various protocols such as HDMI, USB, Ethernet, BT, BLE, based on whatever the version of the Raspberry Pi you are using. Then Raspberry Pi has an environment. And when I say environment, It works with the Linux operating system, and you need to know various Linux-based development environments, Linux-based the tools, whatever is required basically to do, basically which will help in your development. So from the programming language perspective, yes, it also supports various languages. So it supports C, C++. It also supports Python. So at a user space programming, you can always use Python here. And Python based IDEs and the code blocks for the C programming IDEs. I think these are some of the things we should know if you want to do a full-fledged programming in Raspberry Pi, or you have to do a peripheral programming in Raspberry Pi. Here, it basically makes use of a typical consumer and producer model. When I say consumer or producer model, if you know Linux, basically it has core driver which is related with the hardware functions. Then you will have a logical driver. Just to give an example, you can have a USB code stack, then you will have various mass storage class or communication class, so various classes, and you will have a core device drivers. So the core device drivers basically provides the interface to speak to the hardware, and the logical drivers will help you to speak to the user applications. So two sides, user application, you will get logical drivers, then you will get the code drivers, then you will get the hardware interface. So the key of the Raspberry Pi programs is the programming languages, as I already told, Python and C, C++, then various debugging methods, the various software test tools, debugging tools. You also need to, sometimes when you do a programming, you also need to do a debugging at a hardware level. So OpenECD is a tool which is used very widely in Raspberry Pi. So if you see the block diagram, you will have basically applications which is based on Python or C. I will show right now in the webinar now. We will have the applications developed in Python. Then you will have a character device file. So then you will have a virtual file system, which is a logical driver. Then you have core driver, then the low level interface, which I explained it to you. So now, in order the user application to use the character drivers, I think you may be knowing, usually in Linux, what we do is we will have a sort of a open, close, IOCTLs, read, write. Those functions, system calls will be used in the user side application. Exactly, that works even here. So you will basically make use of an open function with a /dev interface. This is basically a character device file. This character device file will be unique for, for various interfaces. For I2C, you will have a character device file. For SPI, you will have a character device file. So like that. Maybe you are already knowing that you will have in Linux, you have network drivers, block drivers, and character drivers. So what I mean by /dev interface is, whenever I am registering any of the device driver, I will get basically in device tree, if I see, I will get a /dev entry for each of those drivers, which I will use in my open functions. So this character device file is nothing but that entry. So that will help me basically to open the logical driver. Then what will happen is that when I do that open the /dev entry, that will actually map to entry points in the linked character device drivers, which basically finally does speaking to the hardware, taking back the data from the hardware and giving it to the user applications. Then what I would like to do here is, I'm actually like, since Raspberry Pi is a pure digital processor, my processor. So what will happen is, actually, if you see in the field, you will have various analog devices, and you will have a current, voltage. All these are basically analog signals. So how you will integrate these analog signals directly to the Raspberry Pi? Raspberry Pi is a pure digital form. So what will happen is, we will have an analog to digital converter in the middle. So in this for this webinar, actually I created a small code which basically an A to D analog to digital converter, which is MCP3008, which is used here. What has happened is, this MCP3008 is connected to Raspberry Pi through SPI interface. If you see here, the connections between ADC and Raspberry Pi are as follows. So if you see the last 6 lines, yeah, you will have a VCC ground, and then you'll have the four major signals, four signals of the SPI interfaces. They are the serial clock, then MISO, then MOSI, and the chip enable. The serial out, serial ins, and the chip enable, and the power supply, VCC, and ground. So the code can be implemented basically using Python as on C, as I described you before. So what I will go through this Raspberry Pi, I have the three potentiometer. What you see are the for the analog to digital the inputs. Then I have a MCP3008, which is an analog to digital converter. Then the Raspberry Pi connected with the power, which the white cable which goes, and through Wi-Fi configuration, I'm speaking to the laptop with the Raspberry Pi, and I'm actually basically like running right now Putty to speak to the hardware, which is Raspberry Pi right now. So Raspberry Pi, we need to give basically the host name, and then the port. We should open this putty so that we will get access to the Raspberry Pi board. Before going to Raspberry Pi, what we have to do is we have to make the SPI enable. So usually all these peripheral interfaces are off. So I have to make the SPI interface first enabled. So for that, there are actually some Raspberry config is basically the tool, I mean the utility, which is used to enable all the GPIOs, all the I2 CSPIs. The GPIO will have input, outputs, directions. We can set all of them using this configuration tool. Once I save these configurations and I will exit, then again it will come to the shell. Then this is the MCP3008 is the code, which basically is a Python code. This basically read the data from the analog to digital converter. And you see, we basically read the MCP3008 data. So since we have 3 channels, so we will be basically reading the 3 channel data here. So, and these 3 channel data, what we have done is for one channel, we have given 5 volt as an input. And for the another 2 channel, 3 volts, 3.2 volts at the maximum input. So that since I am using a potentiometer, you will see basically when I rotate the potentiometer, you will see a voltage varies from 0 to 5 volt in one analog channel, and in another 2 channel it will vary from 0 to 3.2 volts. So if you see here, the first channel, it is showing 5 volts. Just trying to vary one of the potentiometers right now. So you should be able to see this varies from 0 to 5 volts. So if you see the first channel, now it is showing 0 volts. The potentiometer, I made it to a lower position. So now I will make it to a little into the middle so that you will see approximately 2.5 volts to 2.9 volts. 5 volts, 4.9 volts. So see, that particular potentiometer is connected between VCC and ground. VCC is 5 volts. So that's how you will see a voltage from 0 to 5 volts. So there is another potentiometer where you will see a voltage varying from 0 to 3.2 volts. So the Raspberry Pi has 2 power points. So one is the 5 volts, another is 3.2 volts. That's why we are able to get these voltages here. Yeah, earlier it was 3.2, now it has become 0. If you see, now it has become almost like 1.67, the second channel, 1.7 volts. So now if you see, the first channel is 5, second channel is 3.2, third channel is again 3.2. So we will do a complete peripheral programming in detail because this is just a webinar. So I just wanted to create very basic Python code. So we will actually go through how to create a C program, basically like how to create a C, how to create a Python code. We will take up various interfaces, I2C, SPI, and all the various type of peripherals, and see how we can do a peripheral programming using Raspberry Pi. Yeah, if you see that project was done on Raspberry Pi peripheral SPI, basically the MC3008, if you see the analog to digital, A to D converter code, basically we had 3 channels, 5 volt and 3.2 volt lead from 0 to 5 volt in one channel and 0 to 3.2 volts in another two channels. And then the Python code is returned basically to read the analog to digital converted out. So how we can do that in Python and how we can do it in C? I think how to do it in C and how to compile. So just wanted to show basically like how the peripheral programming classes. If you see your college project, right, engineering or whatever the projects you were handled. So initially we were working only on the products. Just to give an example, okay, I want to do a odometer design, I want to make a speedometer design, I want to do a water level controller. We used to do a product design. Then what happened is slowly we started looking into the smart product. So when I say smart product, even if you take the fridge as an example. So earlier we were only using the fridge for cooling. Then some additions were attached, like smart cooling. So it is basically like based on, along with the smart cooling, you also see that, okay, if there is a milk container in the fridge, so if it goes below certain level, then it gives you an alert saying that, okay, milk is getting empty soon. So like even in the vehicles, if you see, you will come to know that, okay, petrol is reached a level where we should actually go and put the petrol. So there are alert systems started coming in the smart product. Then they wanted to take it to a bigger level. So they started making a smart connected product so that these alerts will directly go to the milk booths. So the evolution happened in terms of smart product and smart connected product. Then actually product system and system of systems. People started putting all this data, Internet of Things data to the cloud, and then do a better analysis in the cloud. And if you take an example today, so when you travel from one place to another, you will see actually like traffic in a scenario like where you have too much of traffic in one particular road. Based on the data which is transmitted from various vehicles, then there is an analytics is happening in the outer cloud, and it gives actually an indication to all the drivers saying that you avoid this road. The changes happen, you will see basically complex in functionality happen. And also if you see the real-time behaviors, we will experience, we are actually like experiencing the real-time behaviors, and which will involve basically a combined hardware and software systems. So various sensors, actuators got integrated with the various distributed software, various computers, and because of the networking, if you take system of systems, which is the last block here, lot of software and hardware components are involved to make the end-to-end system. So when this evolution happened, then what are the challenges and the complexities? Complexity in terms of software development got increased. So now how to mitigate them? So there are a lot of new evolution happened in terms of the programming languages. A lot of evolution happened in terms of software and hardware design methodologies. A lot of improvements happened in the operating system requirements, real-time operating system features. In order to do this, then I also need to do, if I want to give an example, if I want to add a new RTOS feature, assume that RTOS is supporting a multi-processor environment. Then I need to have my debugging tool also to support me to do a multi-processor environment debugging. So if you see, everywhere the changes happened, everywhere the complexity increased and the improvements happened. See, there are three type of challenges I am seeing. One, from studying, it was all domain. I have done my electronics and communication engineering. So at the top level, it is electronics and communication. That is the domain. That is the field. Now, but if you see today, and whatever I studied in electronics communication, I may not be using it today, if you frankly ask me. So, but at that time, all the engineers were either civil, electronics and communication, computer science is a limited number of fields. So now what is happening is I could see a shift from branch to a skill-based jobs. If you ask me today, let's take various semiconductor companies today in our list. They also don't want complete electronics and communication in their projects. They either need, or some group need only firmware developers, some group need only the test and validation guys, some group really need only the real-time operating guys, some group really need only hardware guys. So we no need to know. It is basically, even if you take an example, if a hardware platform supports say FreeRTOS, Linux and various operating systems, then from engineering, if you see the top to bottom, now I am making my team focused for Linux, for RTOS, for ARM, for x86. I started making small pieces in my team itself. So what happened is, now the career path, if you see the job opportunities, if you see, there are so many varieties. Even the freshers, if you take corporate as an example, corporates want exact match of what they need. Earlier, it was not. If you know electronics communication, if you know C programming, they used to take. But it is not so, right? Not so. If you know Java programming only, they will take. If you know C programming, then only they will take. If you know Linux, then only they will take. So that skill level search engines and searching and the evaluation method, not that is actually playing a major role. And that's how these training, if you see, there are a lot of freshers, there are a lot of junior profiles are available in the pool. If you take a services company, there are a lot of engineers are on the bench. If you see the the semiconductor companies, they are not able to find the exact match for the requirement. The resource pool is available in the services companies as well as in the market. Still, the exact match is not seen. This primary reason is because we are moving from branch, what you call electronics communication, electrical and electronics, from branch to the skill based training. I think we need to actually somehow fix this. I think such trainings, what will happen is, will really help. See, now if I want to work in a firmware, then if I know all these interfaces like Raspberry Pi, because I took Raspberry Pi because of Linux experience you will get here. You will get the core device driver experience. You will get Python and C experience. These are all some of the key experiences required for a firmware engineer. You should know wherever you go. These are the typical skills which you definitely need for a firmware engineer. As I said here, technically, the focus while hiring in the recent past is slowly moving from technology to skill based. I think freshers are finding little challenge in getting the core companies like semiconductor companies, and even in the core companies are not getting the exact skills. So there is a gap. So I think such trainings will basically help in fixing these gaps. So I think I told in my each of these points in various other slides, digital and analog electronics is mandatory, because if I want to integrate any peripheral, I should know what is the type of signal it is, whether it is digital or analog. If you see today, I took A to D 8-channel project, small project, which basically, because I wanted to connect an analog signal to the Raspberry Pi. That's so all this digital to analog electronics is mandatory, and we should understand the schematics. If I want to write a device driver code, or if I want to write a firmware code, I need to know, then definitely see programming. RTOS and RTOS internals. Then we also should know the various memory regions, stack, heap, and IVTs. Then various peripherals, their internals, and various debugging tools. So yeah, that's it.